Hello friends, welcome back to the series on physics of solids. In the previous talks, we discussed about the arrangement of atoms in a lattice. We saw different terminologies and methodologies to understand the crystal structure. We also told that the properties of solids are mainly decided by its constituent atoms and its arrangement. In studying crystal structures, in our earlier sessions on physics of solids, we have assumed that atoms were at rest at their respective lattice sites. Atoms, however, are not quiet or they cannot be assumed to be completely at rest because of different reasons. One of the quick reasons one can remember could be that about its stability, which is suddenly is being suggested by different quantum mechanical models. So, definitely they will be oscillating about their equilibrium positions as a result of many energies, of which the most important one could be categorized into as thermal energy. So, while categorizing them into thermal energy does not mean that you have to really supply an energy. Any energy above the 0 Kelvin can contribute to an oscillation, and you know that no substance can be brought to the absolute 0 or the 0 Kelvin temperature. Therefore, there will be definitely an oscillation around their equilibrium positions as a result of thermal energy. So, in fact, we have to deal with this kind of oscillations in a much more better or in a bigger manner, because the properties of the crystals or the properties of solids are very much dependent on these kind of oscillations also. But I should be telling you that definitely the crystal structure is important, the lattice structure is important, and also its constituent atoms are also important. But the oscillation of these atoms about their atomic or lattice points cannot be discarded, or they cannot be made into a separate cabinet. One has to deal with this kind of vibrations also at the same time when we deal with the crystal structure, whenever we deal with the advanced properties of any solid. So, therefore, in the next few lectures in this series, we will be discussing these lattice vibrations in detail and include their influence on the thermal, acoustic and optical properties of the crystals. So, let us start the journey there. So, now the properties of solids can be roughly divided into phenomena that are related to two different actions. Number 1, the motion of the atoms around their equilibrium positions, and those which are determined by electrons. So, there can be different ways of classification of the basic or the fundamental phenomenon behind the properties of solids, but one of the divisions could be based on the motion of the atoms or the motion of the electrons. So, this division is justifiable since the motion of the nuclei is much slower, because one can straight away think that the nuclear vibrations are also significant. Why not put them into as a third category? Because of the larger mass of the nuclei, definitely you can assume that the motion of the nuclei is much slower than the electron motion. But in this division itself, in this two class division itself, the part related to motion of electrons can be is found to be more related to the phenomena like electrical conductivity or the resistivity of a material. So, in this session we will not be dealing with the kind of properties which are coming up, or the understanding of the motion of the electrons in a solid. We will more concentrate on the motion of the atoms about their equilibrium position in a crystal. Broadly, this kind of vibrations can be categorized into one single terminology, say people call it the lattice vibrations. So, basically lattice vibrations can explain different set of physical properties. One of them could be the sound velocity, how a sound travels through a solid. So, sound velocity is rather dependent on the lattice vibration. And then a class of thermal properties like specific heat capacity, thermal expansion, or say thermal conductivity, which is very much valid for the materials like semiconductors or the insulators. And then there is a different class of properties which comes under the elastic properties, such as say hardness, Young's modulus, the temperature dependence of the elastic constants, a whole such properties. And then there are a different class of properties which comes under the optical properties. For example, infrared absorption. How does a light, how can you develop an understanding of the absorption of a light into a material? So, all for developing a basic understanding or the physical understanding of all those phenomena, one basic thing to study about is the lattice vibrations. So, therefore, the study of lattice vibrations gains much more importance. Now, what is lattice modes of vibration, right? In a normal situation, the atoms in a crystal are bound to each other, right? How? Because in our classes earlier, in our sessions earlier, we already told that the atoms definitely are having definite positions or the definite basis points about a lattice, right. So, although there is no physical or a bond or a chain connecting them each other which is visible to a naked eye, but internal to that there is in fact some kind of a electrostatic origin kind of bond which are present in every crystal lattice, which puts these atoms bound to each other. So, what is the nature of those bonds? The nature of those bonds can easily be generalized into a spring like bonds, because these atoms do vibrate with respect to each other, and they do get back to their positions or they do go away from each other. Therefore, we can assume approximate a bond into a spring like system. So, in a classical way, when we see when we try to understand this lattice modes of vibration, generally we start with a spring like bond system. Therefore, the motion in one atom will induce a collective motion in all the atoms of the crystal in the form of a elastic wave, which is very clear, which can be very clearly understood, because whenever 2 or 3 or many more atoms or any bodies are connected to a spring, whenever you make a vibration on one single ball, that can generate a corresponding vibration in all the parts of that spring, where all the bodies which are connected to that spring system. So, these kind of vibrations are in general categorized into normal modes of vibration, and each normal mode has its own frequency and direction of propagation, right. Because I am talking about a crystal structure which is connected with which is made up of different atoms and different springs which are attaching them with each other can have different modes of vibration. They can have different frequencies, but these different frequencies might be acting in different directions, right. Because in crystal there is no it does have different directions. It does have say like 100, 111, 110, all these kind of directions are possible, which we dealt with when we talked about the Brillouin, when we talked about the reciprocal lattices. So, these kind of different symmetry directions will be there, and each each symmetry directions could have different normal modes of vibration. But one thing to categorize a normal mode of vibration is that each normal mode has its own frequency and direction of propagation. So, now let us take the case of a of an atom, atomic system of say n atoms, right, n number of atoms, capital N number of atoms are there, and you assume that there are 3 degrees of freedom which you allow for the system. So, now the question is that how many normal vibrations are possible in the crystal? Answer would be 3n, right, because n atoms, 3 degrees of freedom, that means 3 into n, 3n normal vibrations. A lattice may be vibrating by its own internal energy or from an external force, which are of mechanical or electromagnetic in origin, right, because as I told in the beginning, the lattice has got to the atoms which are present in the lattice has got to vibrate. It cannot stop vibration because of its stability reasons. But in addition to that, when you apply as a temperature or an optical radiation into a lattice, that will be putting up an external force on the lattice, so that it can make further vibrations. Now, in order to understand this kind of normal modes of vibration, like in any derivation in physics goes, we start with a very much with an imaginary system which is of a monatomic lattice. So, our learning outcomes of this of the study on the vibrations of monatomic lattice could be: 1, to find the frequency of an elastic wave in a monatomic lattice in terms of the wave vector and its elastic constants. Second is to plot the dispersion plot for a monatomic lattice vibration. Here we consider the vibrations in a crystal with only one atom in the unit cell, right. So, there are different cases of crystals which you can imagine where you have only one atom in the unit cell or in the primitive unit cell. Assume that we are considering a high symmetry axis, say 1 1 1 direction, along with the so called wave. Wave means here we are assuming the elastic wave, right, because we are assuming that all these atoms are connected to each other by springs. On propagation of the wave, the entire planes of the atoms moves in phase with displacements either parallel or perpendicular to the direction of the wave vector, right, because this is very easy to understand when you know about the so called 2 classes of waves called longitudinal and transverse waves, which I will be touching up in few moments time. So, basically if we generate a vibration on one of those lattice points, the displacements could be generated either in the parallel or the perpendicular to the direction of wave vector. So, therefore, in such a situation you can assume that the so called the vibration of the monatomic lattice, the whole system can be assumed to be reducing to find the expression for a one dimensional monatomic lattice. As you can see in the image, let us assume that you have got atoms which I denote it by the names n, n plus 1, n plus 2, or to the other side n minus 1, n minus 2, etc. And the forces are assumed to happen only between the nearest neighbors for our easiness of our derivation. And the mass of each of the atom is assumed to be same, every atom is assumed to be the same, and let us put it as capital M, and the separation between the atoms be A. and we assume that the elastic response of the crystal is a linear function of the forces, right, because that is generally what we do when we deal with any spring system, F is equal to k into x, right. And then the position x of the nth atom can be assumed to be n into a, right, because a is the distance between two different atoms. And for the n plus 1th atom, x is equal to n plus 1 into a, etc. So, that will for n minus 1 the atom, the x will be n minus 1 into a, etc. Now, here we need to introduce a new parameter or the quantity which I denoted by the un. So, what is un? Un is the position vector of the nth atom with respect to equilibrium. One should be very careful in noting that un is not the absolute position vector. Un is simply the position vector of nth atom with respect to its equilibrium position. So, that can vary depending on the kind of vibrations which you generate. And correspondingly, there are other atoms as we named it as n, n plus 1, etc. Those are therefore correspondingly we can designate those position vectors by the letters un plus 1, un minus 1, etc. But all those are position vector with respect to equilibrium. So, that will be clear more from the image which is shown here. And so, now you know we started with the agreement that we will go with the linear kind of displacements. So, let us write the effective force on a particular atom, say n. So, what will be the expression? F n is equal to beta, beta is the force constant. Generally we denote it by k, purposefully avoided the force constant to be denoting by k in this session, because there are various other k which is coming, which is k which is related to the wave vector, and you have the k which is related to the Brillouin zone. So, let us avoid that confusion. So, purposefully I put the elastic constant or the force constant to be denoted by beta. So, F n is equal to beta into the displacement. So, what is the displacement for the atom n, which is un plus 1 minus un plus un minus 1 minus un, right. Nth atom has got two displacement, one with respect to the atom n minus 1 and another with respect to the atom n plus 1, which is un plus 1 minus un plus un minus 1 minus un. And then what do you do next? This is all steps which we must have done in our earlier classes. So, the equation of motion we have to write. So, equation of motion is F is equal to m into, so if I take it as del m into del squared un divided by del t squared, which is equal to beta into un plus 1 minus 2 un plus un minus 1. So, in the second equation, which was the equation of motion, we can straight away assume a solution, right. So, what is the kind of assumption which will you do? There is a very familiar equation which we normally call it as the wave equation, right, the travelling wave solution. So, connecting to that travelling wave equation or the travelling wave solution, I can put it as un is equal to u0 into exponential of I into omega t minus k in k n a. So, is there any parameter which we have not told about? N is the denotation, is the way in which we denote the atom. A is the distance, k is the wave vector, omega is the frequency. Yeah, that is it. So, and the u0 is the amplitude, right. So, we have assumed the a solution for the second equation, equation number 2, and correspondingly corresponding to un, we can have other solutions also being assumed for un plus 1 and un minus 1. So, un plus 1 is equal to u0 into exponential I of omega t minus k into n plus 1 a, un minus 1 is equal to u0 into exponential I of omega t minus k n minus 1 a. So, those are the, so now you know un plus 1 and un minus 1. So, let us substitute these equations, equation which we un plus 1 and un minus 1 into the equation number 2, right, which is the equation of motion. So, m into dou squared u by dou t squared. So, there we put the un. So, m into dou squared by dou t squared of u0 exponential I omega t minus k n a is equal to, so if we solve that part of the equation, you will reach that m into I squared omega squared un is equal to minus of m omega squared un. And if we go into the right hand side of the second equation, where we had un plus 1, 2 un and the un minus 1, and we substitute all those things into the right hand side of the equation number 2, we can straight away assume it to be equal to 2 beta n into 1 minus cos k a, because we from where does this cos k came, because exponential of minus I k a plus exponential I k a can be connected to cos k a. So, therefore, m omega squared un is equal to 2 beta un into 1 minus cos k. Therefore, that can be simplified as m omega squared is equal to 2 beta into 1 minus cos k. Now, we can assume an expansion for 1 minus cos k a, which is in terms of the cos squared and the sin squared parameters. So, one is so therefore, 2 beta into cos squared k by 2 plus sin squared k by 2 minus, then for the cos k, cos squared k by 2 plus sin squared k by 2, which can be simplified as omega squared is equal to 2 beta by m into 2 sin squared k by 2, or omega is equal to plus or minus 2 root of beta by m sin k by 2, or we can straight away write omega is equal to 2 omega m into sin k by 2. So, what is omega m? Omega m is the maximum value of omega. What is omega? Omega is the frequency with which the normal mode of vibration which we started assuming in the beginning of your derivation. Now, we know that k is equal to k, which is the wave vector. Wave vector is equal to 2 pi by lambda, inverse proportional of the wavelength, right. Now, in the long wavelength limit means smaller frequency, right. What will happen to k? K a will be very small. Therefore, the equation number 5, where omega is equal to plus or minus 2 into root of beta by m sin k a by 2. So, if we assume the k a to be very small, we can approximate the sin k a by 2 to 2 into k a by 2, right. So, therefore, the expression for omega will get modified as 2 into root of beta by m k a by 2, or is this equal to root of beta by m into k a. So, this expression for the omega can be expressed in terms of velocity, right. because you know that omega is equal to 2 pi into frequency nu. Nu is equal to velocity by wavelength. So, 2 pi into V by lambda, which is actually equal, which means equal to 2 pi by lambda into velocity, right. So, what is the expression for our omega? When we assume that it is the long wavelength limit, omega is equal to root of beta by m into K A, which is equal to V into K, because 2 pi by lambda is equal to K, and therefore, that equation can be equated into V into K, and therefore, in the long wavelength limit, the velocity of the wave, velocity of the elastic wave can be found out to be root of beta by m into A. So, what is beta? Beta is the force constant, elastic constant, m is the mass of one single atom, which we assume to be vibrating, and A is the interatomic distance. And we know that in a linear lattice there is an expression connecting the velocity and the Young's modulus. So, V is equal to root of y by rho, where rho is the density. So, our new expression for the velocity, which is root of beta by m into A, can be equated to root of y by rho, or which means that the expression for for omega 2 into root of beta by m sin k by 2, the root of beta by k m can be substituted with y by rho, and it can be found out to be 2 by A into root of y by rho sin k by 2. So, what we achieved? We have connected the frequency with the frequency of the single mode of vibration with Young's modulus and the frequency, or which can be connected to the sound velocity, right, because sound velocity is root of y by rho. So, therefore, the expression can be simplified as omega is equal to 2 into 2 by A V s, velocity of sound, into sin k by 2, which is very which is a very useful expression. So, now we have two expressions. One is at the long wavelength limit, we have omega is equal to root of beta by m k A, and in the general case we have omega is equal to 2 into root of beta by m sin k by 2. Now, we need to deal with the dispersion plot, and we need to discuss how does this how does the phase velocity and group velocity of this system will modify based on the input signal which we put. And we should be seeing higher order atoms, which now we are assuming one single atom in one lattice. In the next session, we will be dealing with those kind of vibrations where we have more number of atoms being assumed in the lattice, and therefore, there will be different set of displacements which has to be assumed at that part. So, we close this session for today. Thanks for watching this session. We meet next time. Thank you.